Hello everyone, this is Dennis and you are on the Den Electro channel. Today we are talking about effective nutrition. I have this uninterruptible power supply. He worked for many years, excellently. Everything is connected, nothing is broken, all working parts. But unfortunately the battery began to run out. The uninterruptible power source was equipped with a lead-acid battery. Here's one for 7 amp hours. Over a long period of operation over several years, it lost more than half of its volume, only 3 amp hours left. As a result, when the electricity was turned off at home and the computer was running on battery power, it only lasted for 10 minutes. To return the uninterruptible power supply to normal operation, it was decided to replace its lead-acid battery with a new lithium iron phosphate one. The new battery will look like this. It'll be installed in the same place where the old battery was. The battery consists of 8 batteries with a total capacity of 12 ampere hours. Today I will tell you how to assemble such a battery, what is needed for this, and how it will work. In this table, I have presented the main characteristics of both types of batteries. The characteristics are naturally generalized, and each manufacturer may have their own. But in general, it is clear that lithium iron phosphate batteries win in all respects. I haven't listed the price here, since it also changes a lot. Previously, lithium iron phosphate batteries were significantly more expensive than lead-acid batteries of the same capacity. But now the prices are almost the same, and there is no point in buying a lead-acid battery. A lithium iron phosphate battery will last for decades, and this is taking into account the fact that it will lose only a few % of capacity. The degradation process will of course accelerate if the battery is cut and drained every day. But in our case, naturally, this will not happen, since the battery is installed without an interrupter and will be in buffer mode. And even if we imagine that someone's electricity goes out every day, the number of charge and discharge cycles is incredibly huge. It will still take years to destroy a battery this way. And if you buy lead-acid batteries, then in the same period of time you will have to change several pieces. I will use these types of lithium iron phosphate batteries, size 32700. Operating voltage 3.2 volts. The maximum voltage recommended by manufacturers is 3.65 volts, and the minimum is 2.5 volts. But the protection board that I will use will discharge the batteries even lower, up to 2.35. Claimed capacity is 7,000 milliamp hours. But in fact, none of the 8 batteries had such a capacity. The minimum was 5,987, and the maximum was 6,215. The discharge current is up to 30 amperes, and the charging current is 3 amperes. Nickel plates are spot welded to both poles. They have a heat shrink tube that can be removed if desired. Before using batteries, their voltage must be equalized. My tensions turned out like this. I charged all the batteries to a voltage of 3.65 volts, but after a day the voltage dropped. There is nothing bad in this, that's how it should be. I charged the batteries with this device, with voltage and current stabilization. Here the batteries are almost fully charged, and therefore the voltage has risen to the end. The current is also already small, and when it drops to 100 milliamps, then, in principle, charging can be considered complete. If you have nothing to charge your batteries, and I think this will happen to many people, then they will have to be thinned out. You can discharge it like this. We take a light bulb and a voltmeter, connect it to the battery and monitor its voltage. We wait until the voltage drops to 2.5 volts and turn off the light bulb. By this time the battery will be almost completely discharged. You can discharge even lower, but I wouldn't recommend it, since the voltage there will decrease very quickly, and a strong discharge can accidentally damage the battery. At the beginning of the discharge, you can take a more powerful light bulb. But at the end, when the voltage approaches 2.5, I recommend taking a weaker light bulb. This way the voltage will drop smoothly and you can turn off the load in time. There is a third method. If you don't want to charge and discharge batteries, you can use the lazy method. You just need to take two bare wires, connect all the positives with one, and connect all the negatives with the other. In this way, some batteries will be discharged while others will be charged, and the voltage will become the same. But I would not recommend it since it is still not very reliable. The fact is that the voltage of these batteries changes very little during operation. From idle voltage to operating voltage, it will drop very quickly, but then it will stand at voltage 3 or 3.2 for a very long time. It will go down, but slowly. Although the battery will lose stored energy, and when there's very little of it left, the voltage will rapidly begin to drop to 2.5. So if the voltage is averaged, and at this time, try to connect them and equalize them. Then their charge capacity may be different. The voltage will become the same, but the charge of the capacitance will be different everywhere. In general, of these three methods, the best and most reliable would be to charge each battery to the maximum voltage. Here you can definitely be sure that the batteries are in the same condition. Then, using electrical tape, the batteries need to be connected in pairs. By the way, it is advisable to take the electrical tape more tightly so that it does not stretch. Otherwise, the whole structure will dangle. Then we also connect all four batteries. Then I lay down a piece of cardboard and fold one contact over. I drop a little acid onto the nickel plate. And then I earn this place. On the second contact, you need to do exactly the same. Then the contacts need to be made so that they are connected in tinned places. I also drip acid on top and tin it. The plates must be pressed well and burned with a soldering iron, so that the tin melts between them. At the same time, I solder the wire. This side was writing. Now you can flip it over and continue from the bottom. Here we do everything using the same technology. Please note that I removed the heat shrink from the contacts. On the other side, I repeat everything exactly the same. Then the wires need to be inserted into the cavities between the batteries and the electrical tape. This way they will stick out on the other side. Well, after thinking a little, I decided to solder the nickel plates more reliably, connecting them in these places. By the way, if you think that batteries get very hot during soldering, then you are mistaken. Nickel plates are very thin and therefore heat up quickly. Therefore, soldering occurs quickly and the batteries do not have time to heat up. Then we turn the batteries upside down again. Lay down the cardboard and wrap it with electrical tape. To ensure that nothing happens to the batteries during operation, you need to use a protection board, BMS. This board will protect each battery from discharge and overcharging. The maximum voltage will be 3.65 and the minimum 2.35. This BMS board is rated for an operating current of 14 amps, but can go up to 20 in short-term use. The batteries of the protection board are connected according to this scheme. The wires marked in yellow should be thick. All the huge current will flow through them. Black wires are signal wires. Using them, the BMS measures the voltage on each battery. There is no large current here. wires can be used very thin. The P plus and P minus terminals connect charging and load. I place the BMS on cardboard and glue it with double-sided tape so that it does not move. I immediately added more tin to the soldering pins to make it easier to solder the wires later. Then the battery contacts need to be bent and soldered to the terminals. The negative to the B terminal is minus, and the positive to B is positive. Solder well, otherwise if the contact area is very small, the contact will heat up. The current here will be up to 15 amperes. Then you need to solder the two side wires to terminals B1 and B3. There is almost no current in these places, but you need to solder thoroughly and carefully. If any wire accidentally falls off and pokes into any part of the board, it will instantly burn out. Also keep in mind that the order in which you solder the wires to the board does not matter. When all ends are connected, the BMS will work immediately. If the battery bars stick out too much, they can be bent, or just shorten it before soldering. Solder the last bottom wire to terminal B2. Well then, if the wires are long, then they can be hidden under electrical tape. The old battery had terminals like this. Here there are two dads, and on the UPS there are two moms. To connect new batteries, you need wire lugs. I also bought them on AliExpress, both dad and mom. Along with them, the set includes transparent cambrics. They come in different sizes. My uninterruptible power supply uses these. Then the wires need to be soldered to the lugs, crimped with ordinary pliers and the cambrics put on. To avoid mixing anything up and burning anything, you can glue colored electrical tape to the wires. Wire cross-section 4 square stranded copper. For a current of 15 amperes, this is sufficient with a margin. Then the wires are soldered to the BMS board and you're pretty much done. The result was a 12-volt battery with 6,000 milliamp hours. It is advisable to use outgoing wires of different lengths so that they do not accidentally short out in bare places. This BMS board does not have short circuit protection at the output, although it is advertised on AliExpress. I relied on this protection and through carelessness, accidentally shorted the wires. This happened for a split second, but the board still burned out. Now I'll tell you how this whole system will work. I'll start with the simple one first. Only batteries and protection board. We have 4 batteries, either completely discharged or fully charged. After a complete discharge, without load, the voltage may rise slightly. For example, after 2.5 it will become 2.7. And after fully charging on the contrary, it will fall. After turning off the voltage, it may drop to 3.6 or slightly lower. It'll be different for all batteries. In this state, we connect them to the BMS protection board. It will monitor the voltage of each battery. This protection board is one of the simplest, and therefore there is no voltage balancing function here. Therefore, even under its control, the batteries will always have different voltages. The maximum voltage will be limited to 3.65 volts, and the minimum to 2.35 volts. Here, of course, there is an error everywhere, plus or minus, and therefore you definitely shouldn't chase the same numbers. Each BMS may charge slightly differently, and your voltmeter may show different numbers too. I charged each battery to maximum voltage. This way, 100% of its capacity is filled. But although the batteries are the same, their capacity is different. For example, we will assume that she is like this. If we connect a load to the board, the batteries will begin to discharge. Due to the fact that the batteries are connected in series, their discharge current will be the same. Therefore, the battery with the smallest capacity will be discharged first. When its voltage drops to 2.35 volts, the BMS will turn off the load. It turns out that the capacity of the entire battery is equal to the capacity of the smallest battery. The first battery was completely discharged minus 5,900 milliamp hours. And the remaining batteries were not completely discharged, but they supplied the current to the load in exactly the same way. However, the voltage of each battery will be different. Their total voltage can be large, but BMS does not look at the total voltage. She looks at the voltage of each jar. As soon as the voltage of one of them drops below a predetermined limit, everything turns off. When charging the entire battery, the situation will be the opposite. The same current will flow through all batteries, and the capacity of all batteries will be filled at the same rate. Each of them will contain 5,900 mAh. While charging, the voltage will begin to rise, and when it reaches 3.65 volts on any of the batteries, charging will turn off. But the voltage of other batteries will be different, since they are not fully charged. But the difference between them, as before, will not be big. As you can see, even without balancing in the BMS board, the whole circuit will work perfectly. But if we take batteries without a voltage equation, we get a very bad situation. Their capacity can vary greatly. For example, one will contain 4,000 mAh and the other 5,000. For the rest, the capacity will be approximately between them and will also differ. The battery that is least charged will discharge very quickly. As a result, the entire battery will only provide 4,000 mAh. And where there were 5,000, there will still be a whole 1,000 left. When charging starts, the fourth battery with the most capacity will be charged first. It will reach 3.65 volts and the BMS will stop charging, and the remaining banks will naturally remain undercharged. Therefore, in this system, it is necessary to use batteries with the same capacity and the same charge level. Otherwise, it will be complete chaos. Now I'll show you how the BMS turns off if one of the batteries is severely discharged. I connected this tester to the output of the board. It will show the total voltage. And with this, I will measure the voltage of each battery separately. At this time, all batteries are almost discharged. The first battery has 2.75 volts. The second is 2.96. The third is 2.8, and the fourth is 2.84. Now I will connect the tester to the one with the lowest voltage. Then I connect a halogen lamp and wait until everything is discharged. When the battery voltage dropped to 2.4 volts, everything turned off. After this, without load, the voltage rises a little as expected. There is now no voltage at the BMS output at all. The payment went into protection. If the load is disconnected, the voltage rises slightly. But when you connect the light bulb back, the voltage drops again. It doesn't hold any load now. For everything to work again, you need to disconnect the entire load, including the multimeter, or recharge the batteries from the power supply. Or wait until the battery charge rises even higher. When we connect the batteries from the BMS board to the uninterruptible power supply, the rules change a little. The UPS charged its battery to a voltage of 14.5 volts. It turned off when the battery voltage dropped to 10.58 volts. Uninterruptible power supply works according to its own system. It will only see the voltage coming out of the BMS board. It cannot see the voltage of each battery. It turns out that it will turn off charging when the total voltage of all batteries reaches 14 volts. It can be assumed that the voltage of each of them will be approximately the same. It turns out that the batteries will not be recharged a little because, as I said earlier, the BMS is trying to charge them to a voltage of 3.65 volts. But this is not a problem, since the battery receives 99% of its charge up to a voltage of 3.4 volts. And the fact that the batteries have not been charged to their maximum voltage does not play a big role here. The same will happen when the battery is discharged. At this time, the voltage of each jar will be approximately this. When their total voltage drops to 10.6 volts, the uninterruptible power supply will turn off. In both cases, during charging and discharging, the process will be controlled by an uninterruptible power supply, because its voltage range is narrower than that of the BMS board. If the worst-case scenario happens and one of the batteries discharges much faster than the others, and their total voltage is more than 10.6 volts, then the BMS will turn off. The same situation may also occur when charging. If the voltage of the batteries is very skewed, and one of them is the fastest to charge to the maximum voltage from the circuit, the batteries will disconnect the BMS board. Protection without an interrupter will not have time to operate, since the total voltage has not reached the required limits. This concludes the first part of the video. In the second part, I will show how to combine two such batteries to increase capacity and conduct a full test of it.